Hi friends, we have got a cantilever beam AD over here and there are loadings acting on the beam as shown in the figure. So the first loading is a uniformly distributed load of load intensity 5 kilonewton per meter is acting on the length of 2 meter and there is a point load of 10 kilonewton acting at point C, which is a distance 1 meter from fixed end D. So we need to draw shear force and bending moment diagram for this particular beam. So in order to solve this particular problem, our first step is to draw free body diagram of this particular beam. So we have got a beam AD. So there will be a uniformly distributed load. So the load intensity is 5 kilonewtons per meter. This is point A and over here the point B. Now at point C, friends, there is a point load of 10 kilonewton acting at point C. So D is the fixed end. So there will be a support reaction acting at this point. So this support reaction will be reaction at point D. I am going to call it as RD. Since it is a cantilever beam and this end is fixed, there shall be a moment reaction acting at point D, and let me call this moment reaction at point D as MD. Now we have to find the support reaction. So at point D there will be the force reaction RD and there will be a moment reaction MD. So we need to calculate force reaction, moment reaction. So to calculate support reaction of the cantilever beam, we shall be using condition of static equilibrium. This is step 1, friends. Therefore, by condition of static equilibrium, summation of vertical forces equals 0, summation of horizontal forces equals 0, and the summation of moment of forces about any particular point you can take, that is equal to 0. Okay, so these three conditions are called as the condition of static equilibrium. Since we don't have any horizontal force acting on this particular beam, so this condition would be ruled out. So now we have this condition, that is vertical forces, and the summation of moment of forces about any point on the beam is going to be 0. So I'll take this condition first. Summation of vertical forces is going to be 0. So I'm going to take upward forces as positive in the sign convention, and the downward force is going to be negative. So this sign convention I'm going to follow, friends. So this is the sign convention I'm going to use. That is upward forces I'm going to take positive and the downward forces I'm going to take negative. So if you see here, we have got a uniformly distributed load of intensity 5 kilonewton per meter acting on the span of 2 meters. So I'll convert this into point load. So when I convert this into point load, it will be something like this, friends. So it is going to be acting at the center and the value is going to be 5 into 2, that is 10 kilonewton. So now for my calculation, I'll be using this point load instead of this uniformly distributed load. Okay. So now this is 10 kilonewton, it is acting downward. So downward I have taken negative. So minus 10 kilonewton, which is acting downward. So this I have taken care. Now this is also 10 kilonewton force acting downward. This is also downward. So minus 10 kilonewtons. And here RD is upward. So plus reaction at point D, and that is going to be 0. So if I simplify this, I'll be getting RD. These two negatives will go on right hand side, become positive. So RD equals 20 kilonewton. Straightforward. So I got force reaction at point D as 20 kilonewtons, which is straightforward, friends. So we can call this as equation 1 for our reference. Okay. Now I can use the second condition, which is this one, friends. The summation of moment of forces about any point is going to be 0. You can take practically any point on the beam. So I will take point A. Summation of moment of forces. So we are considering moment of forces about point A. So I'm going to put this point A as a hinge point, and then let's apply the forces. So due to application of this 10 kilonewton, your beam is going to rotate in this sense, like this, in the clockwise sense, friends. Okay. So I'm going to follow sign convention here, and the sign convention is the clockwise moment is taken as positive and the anti-clockwise moment is going to be taken as negative. So this sign convention I'm going to follow for bending moments. Kindly remember this. Okay. So this 10 kilonewton, which is the equivalent point load of this uniformly distributed load, this will rotate the beam in the clockwise sense. Therefore 10 into distance will be always, so this distance is always half because it is acting at the center, going to be 1 meter, friends. So 10 into 1 meter is going to come here, that is positive. So 10 into 1. Now this 10 kilonewton will also rotate beam in the same clockwise direction like this. So its distance from point A is going to be 2 plus 1, that is 3. That is again positive. So 10 into 3, and this is another clockwise moment acting on the beam, so this will produce clockwise rotation of the beam. So I'm going to call it as positive again, positive MD. But this RD is going to rotate beam in the anti-clockwise sense, something like this. So this is going to be negative. So RD into this distance, that is AD, is 2 plus 1 plus 1, that is 4. So that is going to be minus RD times 4, and that is going to be 0, friends. If we simplify this, what I'll get is this is 10 plus 30 plus MD minus RD. We have already got the value 20 into 4 equals 0. So now I'll simplify this. So if I simplify this, I'll be getting MD, that is moment reaction at point D, that is MD, we are going to get as this 20 into 4 will be 80, will go on right hand side, become positive, and 10 plus 30 will be 40. So 80 minus 40, as you can see, this is 80, this is 40. So 40 minus 80 is going to be minus 40, will go on that side, becomes 40. So I'll be getting from here MD, that is moment reaction at point D, will be 40 kilonewtons meter. Okay, so friends, if you look at here, we got the value of moment reaction, that is MD, as 40 kilonewton meter, and we got the force reaction, that is RD, as 20 kilonewton. So we got the value of support reaction, that is RD and MD. So now we have completed the step 1 where we have calculated the support reaction. So now we'll talk about step 2, friends. So in the step 2, we shall be calculating the shear forces at various points. Okay, so as you can see here, we have drawn the free body diagram. So we shall calculate the shear forces at various points. So before going for calculation of shear forces, we will do the sign convention. Let me explain you the sign convention we are going to follow. So suppose we have plane like this, friends. So if the shear force is acting in the upward direction in the left hand side of the plane, then this particular shear force is taken as positive. Similarly, if you have plane like this and the shear force is acting left hand side to this particular plane and acting in the downward direction, so this is taken as negative. So this one is taken as positive shear force, while this one is taken as negative shear force, friend. Okay. Similarly, if the shear force acts to the right of this particular plane in the downward direction, this way, this is also taken as positive. And here also, if shear force is acting to the right side of the plane but in the upward direction like this, so this is also taken as negative. So kindly remember, we shall be keeping our shear forces to the left side of the reference plane. So here we shall be moving from left side to the right side on this particular beam, and we'll be considering planes at various sections. Okay, since we are moving from left to right on this particular beam, so if we consider any particular plane, we'll be considering the shear forces left side to that particular plane. So let me show you the example. You will understand with the help of example easily. So I'm going to take point A. Let's say shear force at point A. Now when we calculate the shear force at point A, we shall be keeping plane just left side of this particular point A, and then we'll be moving towards right side and we'll be just crossing the point A like this. So there are two possibilities of planes. So plane may be just left to that particular point A, or it may be just right to the particular point A. Okay, so there are two possibilities. One possibility is when we take plane just left to the point A, and second possibility is we'll take plane just right to the point A. So there are two possibilities of shear forces. So when your plane is here and we are looking in the left hand side of the particular plane, so there is no shear force acting over here. So shear force over here is going to be 0 because there is no force acting over here. So I'll say shear force at 0. So first condition, shear force at point A just left signifies that plane is just left side of this particular point A. So it is going to be 0 kilonewton because there is no shear force acting. The next possibility is we keep our plane just right. So in that case also, friends, there is no shear force acting because there is no force acting to the left of this particular section plane, what I have shown over here. You can see there is small portion of uniformly distributed load is acting over here, but that will be insignificant, friends. So that also will be 0, as you can see here. Now friends, if you see here, there is a UDL, uniformly distributed load, acting from point A to point B. So as I move this particular plane towards right, you will see that the shear forces are going to change continuously due to this uniformly distributed load acting from point A to B. So for that, to get the variation of shear forces due to uniformly distributed load, I am going to consider my plane somewhere in between. Let's say I am considering plane somewhere here. So let's say this is my XX plane I am considering here at distance small x from point A, like this. So it is a variable distance, we can say. So as we move from A to B, this value of x is going to change. So I have considered a plane XX somewhere in between A and B, that I'll write down here. So we have considered a plane XX at distance x from point A. Okay, so now we can find out the shear force acting at this particular location. Okay, so shear force at plane XX. So let's find the expression for that. So shear force, I'll be writing shear force at x. So if you see here, friends, this much portion of uniformly distributed load would cause shear force at this particular plane. So we'll convert this much portion of uniformly distributed load into point load, and that value would come as load intensity, that is 5 kilonewton into distance x. So it is going to be 5 times x. Okay, and it will be acting at the distance x by 2 from point A. So this distance would be, friends, x by 2, because it is uniformly distributed load. So now I'll be considering this particular load. So shear force at section XX would be simply 5 into x. You can see here we don't have any other force acting over here, right? So because of this only there will be shear force at section XX. So this we got the expression. Now, so you can see that the shear force is varying linearly with distance x. This is called as linear variation. So as far as linear variation is concerned, with the help of this expression, I can find out shear force at point A, which we have already got, friends, and we can also find shear force at B. So friends, this indicates the expression of shear forces from point A to B. Okay, so in that case, if I want to find shear force at point A, I have to put value of x equal to, here x will be what, friends? So at this point your x is going to be 0, and if I want to find shear force at B, I have to put x equal to what, friends? 2 meters. So putting x equal to 0 and x equal to 2 will give you the value of shear forces at point A and point B. At point A, there is no point load acting, but there is a uniformly distributed load acting. There will not be any sudden variation of shear forces. So just by taking shear force at point A would give you the values by using this particular expression. So I'll find out the shear force at point A. This is the linear variation. If I find shear force at A and shear force at B, I will be able to get the variation of shear forces because the variation is linear. Okay. Now please remember, when you are finding shear force at point B, we are keeping our plane over here, and this shear force is acting like this, friend. This is the shear force. So this uniformly distributed load is causing shear force for this particular plane, which is at point B. So this force is acting like this. This uniformly distributed load force is acting like this, which is 10 kilonewton, friends. So by sign convention, this is our plane. You can see here, this is the plane, right, which is this XX plane, you can say, and your force, shear force, is acting at the left hand side of this particular plane, we can say, right, and it is acting downward direction. So downward I have taken negative. This will be negative shear force. So this is going to be negative. Can you remember? Okay, as per sign convention. Now, having said that, I will have to find shear force variation at point C, because there is a point load acting at point C, friends. So we shall be considering a plane just before point C, that is just left, and a plane just after point C, that is just right. This is I'm going to follow because there is a point load acting over here. So let's see what shear force we get. So I'll write down shear force at point C. Since there is a point load acting at point C, we will have to take just left and just right. So just left of the point C, and we will also take just right of the point C. So when you take just left of the point C, it means your plane is here. So here the shear force will be caused by, friends, all this uniformly distributed load, and that value is nothing but 5 into 2, that is 10. So obviously for this particular plane, this much force is causing, this much force, friends, is causing the shear force. That value is going to be 10 kilonewton acting downward, and if you have plane and the force is acting downward in the left hand side of the plane, it is taken as negative. So by this sign convention, it is also going to be minus 10 kilonewton. Now let's see the next case. When your plane is just right side of this particular point C, we can say, so in that situation the shear force will be caused by this 10 kilonewton acting downward, so it is minus, and we have got another force, point load, acting downward, that is 10 kilonewton. So this is also minus as per the sign convention. Okay, so it is also minus. So if I combine this, I am going to get minus 20 kilonewtons, friends. Okay, that's a very simple calculation we got. So now we will move towards point D, and our reference plane and our section plane would be just before point D, friends. The shear forces will be caused by this, that is 10 kilonewton, and this one, friends, that is 10 kilonewton. So minus 10 and minus 10 is going to minus 20, which we have already got here. Okay, so I'll write down that. So shear force at point D, there are two situations as we know, because there is a point load, that is reaction at D is acting. So we will have to write down just left and just right. Okay, when your plane is just before or just left of the point D, and the next case is when it is just right of the point D, like this, friends. Okay, so when your plane is just before point D, the shear force will be caused by this, that is 10 kilonewton downward, 10 kilonewton downward. So overall is minus 20 kilonewton downward, that is overall is minus 20 kilonewton, which we have already got over here, which is at point C. So at point C and point up to just left of the point D, the value of shear force is going to be same. But as you cross the point D and go towards right, this force, this is RD, will be included, which is acting upward. So now it will be minus 20, which is downward, and then plus RD, which is upward, which is again 20 kilonewton. So you will be getting shear force at point D just right is going to be 0 kilonewton, friends. Okay, right? So it is going to be 0 kilonewton. So we got the variation of shear forces as we go from point A to point D from left to right. Okay, so I hope this has been understood, how to calculate the shear forces at various points of the beam. So this was the step 2. Now we shall proceed for the step 3, where we calculate the bending moments at various points of the beam. So friends, I have drawn the free body diagram of the beam over here. So support reaction RD we got as 20 kilonewton, and support moment reaction, that is MD, we got at 40 kilonewton meter. So this already we have done, friends. Now we need to find the variation of bending moments. So here also we will be moving from point A to point D from left to right. So there is a sign convention we are going to follow. So let me explain you sign convention for bending moment, friends. If due to application of various forces or moments, your beam is bending in this way, friends. So this is called as sagging of beam. So this kind of bending moment is taken as positive, friends. This is called as positive bending moment. And if due to application of various forces, your beam is bending like this, okay, so this is called as negative bending moment, negative bending moment. So kindly remember, so if your beam is bending like this, we'll be taking it as positive, and if your beam is bending like this, we'll be taking it as negative. Okay, so let's start, and we are going to move from point A to point D from left to right. So I'll take first bending moment at point A. So bending moment at point A. So you can see that if you keep section over here, let's say, so there is no force acting over here. So if no force is acting over here, friends, there is no force acting over here, it would not cause any kind of moment at point A. So bending moment at point A is going to be 0 kilonewton meter, straightforward. Now, so as we move from point A to point B like this, for example, we take planes in between somewhere like this. So you will see that at various points, there will be different forces. These forces are going to change, okay? And these forces are going to cause different moments at the sections. These moments are going to change continuously because there is a uniformly distributed load acting between point A and B. So let's consider one plane in between like this. Let me call this plane as XX, and this plane is at distance small x from point A. So here we have taken a plane XX at distance x from point A, and we would like to find the expression of bending moment at this particular plane XX in terms of the distance x, and then if you change the value of x, we can easily find out the value of bending moments at various locations between point A and B. So the expression would be something like this, that is bending moment at section XX, okay, which is at distance x from point A, is given as, let's get the expression, friends. Now if you see here, this much portion of uniformly distributed load is going to cause bending moment at section XX. We can convert this much uniformly distributed load into point load, and that value would be The load intensity is 5 and distance is x, so it is going to be 5 times x. Okay, so this point load 5x is going to act at a distance x by 2 from point A, because the point load equivalent of uniformly distributed load always act as the midpoint of the length on which uniformly distributed load is acting. So uniformly distributed load I have taken over the span of x, so the point load would act at distance x by 2 as I have shown here, right? So if this is x by 2, this is also going to be, friends, x by 2, as you can see from figure itself, right? So now I want to find bending moment at this particular section or at this particular plane. So bending moment at section xx is given as, I'm writing suffix x to represent it is at distance x. So this much force is going to cause the bending moment at section x. So because of this force, your beam is going to bend something like this. Hypothetically, I'm drawing here, right? Because this force will be bending the beam in this direction, friends. This is the example of this kind of bending, okay, this is called as hogging of the beam. So it is negative bending moment, friends. So it has been minus, now the force is 5x, which is point load equivalent of uniformly distributed load over this particular length, into its distance from this particular plane is going to be x by 2. So x by 2. There is no other force acting, so only bending moment is caused by this particular force. So if I simplify this expression, I'll be getting minus 5 by 2 x square. So this is second degree variation, as you can see from the expression itself. This is second degree curve. Now we are aware that to represent any curve which is having second degree, we require at least 3 points. So if I find bending moment at point A and point B, that is 2 points, I will not be able to get proper distribution. So I should get at least 3 points. Okay, so what we can do is we can divide this particular length AB into 4 equal parts having 0.5 meter length of each part. Okay, so let's do that. So we can say we start from here. So here x is going to be 0, here x is going to be 0.5, here I can take x equal to 1, 1.5 and then 2. So we got 1, 2, 3, 4, 5 points. So it will be easy for us to get proper variation of the curve because the curve is second degree curve. Please remember, for second degree curve we require at least 3 points, okay, in order to draw the curve. So here we are taking 5 points in order to get proper variation. So I am going to get the bending moments corresponding to point A, point B, and these 3 points in between. Let me name these points. Let me call this point as point E, this point as point F, this is point G. Okay, you can take more number of points or less number of points, but minimum number of points required are 3. So I have taken 1, 2, 3, 4, 5 points. As per your convenience, you can take number of points. So we have got expression for point and bending moments. So we have point A, friends, then we have point E, let's say, point F, point G and point B. So when we talk about point A, for that x is going to be 0. For point E, x is going to be 0.5 meters. For F, x is going to be 1 meter. For G, x is going to be 1.5 meters. And then for B, x is going to be 2 meters. So we will substitute the value of x in this expression, that is minus 5 by 2 x square, and we will get the value of bending moment corresponding to the point. So at point A, friends, we will put x equal to 0. So the bending moment is going to be 0. At C, we are going to put value of x as 0.5. So it is going to be minus 5 by 2 and then 0.5 square. And if you simplify this value, it is going to be minus 0.625 kilonewton meters. Similarly, at point F, this point, your x is going to be 1. Okay, from A to F the distance is 1. So we will be writing expression 5 by 2 times 1 square, and that value will turn out to be minus 2.5 kilonewtons meter. At x equal to 1.5, that is point G, the expression is going to be 5 by 2 into 1.5 square, friends. So this value is going to be minus 5.625. Now at point B, we have x equal to 2. So 5 by 2 into 2 square, and that value is going to be minus 10 kilonewton meter. So we got the value of bending moments from point A to point B. Now we shall be taking the bending moment at point C. So let's see how much the bending moment we get at point C. So bending moment at point C, this point, friends. So at this, when your section is at this particular point over here, we can say, so the bending moment will be first caused by this uniformly distributed load. So we know that the uniformly distributed load we can convert into point load, friends. So this is going to be, that is 5 into distance 2, so it is going to be 10 kilonewtons. Okay, now we'll consider only point load. So this 10 kilonewton would cause bending moment at point C, and that is going to be 10 into the distance. Distance is from here at center, this distance is 1 meter, friends, right? So 1 meter plus 1 meter, 2 meter, so it is going to be 5 into 2 meters. Okay, and the beam is going to bend something like this. So this is going to be negative bending moment, we can say, right? So this 10 kilonewton point load equivalent of uniformly distributed load would cause negative bending moment at point C, and the value is going to be 10 into this distance, that is 2 meters. Okay, so minus 10 into 2 meters. So we have considered this uniformly distributed load. Now, so there is no other force which would cause the bending moment at point C, because 10 kilonewton, this point load is acting at the same point C, so it will not cause any bending moment. Okay, so this is going to be the bending moment acting at point C. So the value would be minus 20 kilonewton meters. That's clear. So now we'll consider bending moment over here, friends, at point D. So if you see here, there is a moment acting at the point D. So whenever there is a moment acting, we will have to consider just left of the point D and just right of the point D. And when we consider just left of the point D, that means this condition, here I will not be considering this moment, which is MD. Okay, but when I consider the plane at just right of this particular point, then I will be considering this particular moment, that is MD equal to 40 kilonewton meters. Okay, so let's write down that bending moment at point D. So here I am considering just left, because we have a moment acting at point D. So whenever such a situation arises that a moment is acting at that point, so in that situation we should take before that point and after that point, that is just left of the point and just right of the point, so that in one situation we will not consider the moment acting at the point, while in the other condition we shall consider. Similarly, during shear forces also, if there is a point load acting, we will be considering before point load and after point load, so that in one condition, when we say just left of the point, we will not consider the load, and when we go just right of the point, then we will consider the load in case of shear forces. So this is very important understanding. So bending moment at point D would be showing you two situations, that is just left of the point D. So when we are just left of the point D, this moment would not come into the picture. Okay, and then next one is just right of the point D. So when we will take section plane just right to the point D, then we will have to consider this particular moment, which is MD. Okay, so let me do it. So if I say at point D, I would like to find bending moment. So the one will be caused by this point load equivalent of uniformly distributed load. So it is 10 kilonewton and it is acting at distance. This is going to be 1 meters. From here to here 1 meter, then another 1 meter, and then 3 meters. So it is going to be 3 meters, and your beam is going to bend this way. So it is, we can say, negative bending moment. So this will be minus 10 kilonewton into distance is 3 meters. 1, 1, 1, so 3 meters. Okay, so we got bending moment due to this particular load. Now we would like to find bending moment due to this particular load. So it is again negative, because it is going to bend beam like this. So minus 10 into distance is 1 meter. So if I simplify this, it is minus 30 and minus 10. So it is going to be minus 40 kilonewton meters. Okay, now if you go just right, so this quantity will be as it is, minus 40 will be as it is. Additional, this particular moment, which is MD, will be acting. So if you can see here, due to application of this moment, your beam is going to bend. If you apply moment like this, your beam is bending in this way, friends. Okay, so this is going to be positive bending moment. So that additional moment would come into the picture, that is plus 40. So that is going to be 0 kilonewton meter. So remember, at point D, just before point D, it will be minus 40 kilonewton meter, and just after D, it will be 0 kilonewton meter. Okay, so at point D, you will be getting two bending moments. One is minus 40, another is 0. So this way, friends, we are able to find the variation of bending moments from point A to point D as we move from point A to D. So now we got the variation of shear forces and the bending moments as we go from point A to point D, and now we can collectively draw the shear force diagram and the bending moment diagram. So let's draw that, friends. shear force diagram and bending moment diagram. So now we'll talk about the step 4, that is we have to draw shear force and bending moment diagram. So I have drawn the free body diagram of the beam over here. Now we would have to show the variation of shear forces and bending moment in the diagram called as shear force and bending moment diagram. So these vertical grid lines, they represent the various locations on the beam. So as you can remember, I have taken the points in between A and B also. So I have taken here, I have taken 1 point, here I have taken 1 point, friends, and here also I have taken 1 point. So this was point E, point F, point G. 3 points I have taken in between point A and B. So these vertical lines represents the various points on the beam. Now I'm going to draw a horizontal line. This horizontal line represents the shear forces, so I'll call it as shear force diagram. And this horizontal line represents the bending moment, so I'll call it as bending moment diagram. So as you can see here, these vertical lines represents the various points on the beam, while these horizontal lines represents the shear forces and bending moment. So we'll plot one by one. Let's say first we'll plot the shear force diagram. So as you can see, we have got shear forces at point A. So we'll go back to our calculation and we'll see what values of shear forces we got. So this is basically the calculation of shear forces. So we got shear force at point A, which is this here, as 0 kilonewton. At point B is minus 10, and at point C we have minus 10 and minus 20. Okay, so A, B, C we have got, friends. Then we also got the shear force at point D, that is minus 20 and then 0. So it goes from 0 to minus 10 from A to B, and then just left of point C it remains minus 10, and just right it becomes minus 20. At D, just left it remains minus 20, and then at right it becomes 0. So these values I'm going to plot, friends. At point A we have shear force as 0 kilonewton. It becomes minus 10 at point B, minus 10 kilonewton. It continues to be minus 10 kilonewton just left to the point C, and at just right, friends, it becomes minus 20 kilonewton. So just right it becomes minus 20. So it remains minus 20 till just left of the point D and becomes 0 and it goes to just right of point D somewhere here. So 0 kilonewton, friends. So I'll show you the variation with the help of a line. So it goes from 0 to minus 10 from point A to B. From point B to just left of point C, it remains minus 10. At point C, if it goes from just left to just right, it goes from minus 10 to minus 20. Just right of point C to just left of point D, it remains minus 20. And when it goes from just left of point D to just right of point D, it goes from minus 20 to 0. So this is the variation of shear forces along the length of the beam. So this diagram is called as shear force diagram. So if you look at here, friends, since the values of shear forces are coming below the horizontal axis, so we have the shear forces as negative value. So we have a negative shear force diagram. So if it is coming below the horizontal axis of SFD or shear force diagram, it is called as negative shear force diagram, friends. Okay. Now similarly, we shall be drawing the bending moment diagrams over this axis called as bending moment diagram axis. So friends, these are the values of bending moments at various points of the beam. So we have bending moment at point A as 0 kilonewton meter. So here the bending moment is 0 kilonewton meter, friends. So bending moment at point E is minus 0.625. So let's say this value is minus 0.625 kilonewton meter. Bending moment at point F is minus 2.5 kilonewton meter. So let's say it's here. Again, the bending moment at point G is minus 5.625, friends, and bending moment at point B is minus 10 kilonewton meters. Okay, so we got variation up to this particular point, that is up to the point B. Now we would like to plot the variation at point C. At point C it is minus 20, friends, so it is somewhere here. Let's say minus 20. Please remember, from point A to B it is a second degree variation. Okay, from here to here it is a second degree variation. From here to here it will be straight line. You'll have to simply connect these 2 points. Okay, because there is no variation inside, so straight whatever ends up here, then we simply connect it over here. Now at point D it is minus 40. So somewhere here it comes as minus 40. Okay, again straight line you have to connect, and then at point D, if you go to right, just right to the point D, you will get again 0. So 0 kilonewton meters. Okay, so it is going to vary in this way, friends. So please remember, from point A to point B, it is a second degree variation, so there will be curve coming over here. So I'll be showing a curve. So it is a second degree curve, friends, and from point B to C, because there is no distributed load between, there is a straight line you have to connect, and then so we got straight line here, and then again it becomes 0, so it is minus 40 to 0. Now here if you see, the bending moment values are coming below the horizontal axis, so we have negative bending moment diagram. Here we have negative bending moment diagram. So we have drawn the shear force diagram as well as bending moment diagram for this particular beam. So this way we can easily draw the shear force and bending moment diagram. Okay, thank you very much.